And so you'll have to forgive me if this episode is a little bit long, because I'm trying to convey some of the most difficult concepts in physics to understand, even for professional physicists who have trained for a decade to understand it. So with that massive caveat, I want to talk about like the real answer for Hawking radiation. For me, it's more work to get this answer across, but to me, it's more satisfying. It makes more sense. I can visualize it better than I can visualize the quote unquote standard picture for Hawking radiation. First, we have to go into the vacuum of space. So we go, pick a patch of space, get rid of all the particles. What do we have? And I've talked about quantum fields before. We have quantum fields saturating all of space-time. There's a field for every particle. There's an electron. There, you see an electron over there, electron over here. There is an electron field that soaks, that permeates, that saturates the entire universe. You see a top quark. Look at that top quark over there. Oh, there's another one over there. All of space-time is soaked and is permeated in a top quark field. So even if you have an empty patch of space, you have this field. Now what's happening is that in the vacuum, in empty space, the fields themselves that are responsible for generating the particles that we know and love are kind of alive. They're buzzing, they're boiling a little bit. Even in the vacuum, even in their lowest energy state where nothing extra is happening, the fields are wibbling, they're wobbling, they're boiling. It's almost the way I like to think about it, and this is not how you ought to think about it, but it's a handy analogy. If you're ever in like a room or a concert and you feel like a buzz, like a hum, like you feel like there's an energy in the air that you can't a sensation that you can't directly feel, but you know like there's an excitement, there's something there. To me, just visually, that's how I like to imagine these quantum fields. You go out in the vacuum of space, far away from every star, every galaxy, no particles, no photons, nothing in your little patch. That little patch of empty space is vibrating with the quantum fields. Most of the time, these quantum fields, when they vibrate, they vibrate up, they excite, they randomly bubble, they boil over. Most of the time, they just go away. Sometimes these quantum fields, when they get perturbed, when they start boiling over, these perturbations, these boilovers, these disturbances can start propagating. They can start traveling from one place to another. When they travel from one place to another, like if I hit a quantum field over there and it moves across the room, that's what I call a particle. If I take the electron field and I hit it, I give it some energy, and it starts waving, it starts moving across from one side of the room to the other. I've created electrons. I've excited. I've given energy to the field, and that energy is transported from one place to another. That is what I call an electron. The electromagnetic field, if I give it energy, that energy propagates from one side of the room to the other. That propagating energy is what I call a photon. That's what I call light. It's disturbances in the field that travel from one place to another. Now, if you remember when I talked about virtual particles, if I vibrate the field, if I give energy to the field and it just goes away, it doesn't travel. Like imagine you're in a pool. Sometimes you can hit the water and the waves travel across the pool. Sometimes you just hit the water and then it just, it dissipates. It goes away. Those are the virtual particles. They're both the same thing. Virtual particles and normal particles are the same thing, except one gets to travel and the other doesn't. And the important thing when it comes to Hawking radiation isn't that it's not about a black hole sitting there in space interacting with virtual particles. It's about something else. It's about the formation of the black hole interacting with the quantum fields. What happens is, say you have vacuum of space, you have big empty patch of space doing its thing, vibrating. It's not really making any sound, but this is an audio podcast. Vacuum of space is fuzzy. It's boiling a little. It's tense. It's nervous. And let's say there's a big cloud of gas and it condenses and forms a black hole. Forms a black hole. Some parts of the field that are vibrating get trapped inside the black hole. They're gone forever. Some sit right at the boundary, like they happen to exist right at the edge of that forming black hole. When the event horizon is first starting to appear, some pieces of the field get right up next to it, like they just vibrate and those vibrations just hang out right at the edge. Now, because of time dilation, remember, if you're near a region of strong gravity, your clock runs slower. Clocks on the surface of the Earth run slower than clocks high above the Earth. Those fields that hang out near the event horizon eventually escape. They make it out, but they could escape 1,000 years into the future, 1 billion years into the future, 1 trillion years into the future. They kind of got caught at that moment of creation of the black hole. When the black hole formed, they got near, and some are right up against that event horizon. And they hang out there. To them, they hang out for like an instant. You know, these vibrations in the quantum field, they bubble up and then they go away, almost instantaneously. So for them, it's an instant. But for us, it could be millions or billions or trillions of years, depending on how close to the event horizon that field little vibration-y thing was. But they eventually escape because they haven't crossed the line of the event horizon. They just hung out near it for a long time. And they eventually escape. That interaction between the vibrating quantum foam that sits in the background and the formation of the black hole can promote some of those temporary vibrations into permanent vibrations. Vibrations that travel, that propagate from one side of the universe to the other. And those vibrations get a boost, they start traveling. We recognize those as particles. We recognize those as real particles. It looks like the black hole is glowing, is emanating particles. What you're seeing is a process that was set in motion when the black hole formed. The formation of the black hole itself temporarily caught some of these vibrations in the quantum field. They are usually temporary, are usually effervescent. Are usually, there goes all the momentum I was building in this little conversation. Are usually effervescent, but they eventually escape a day after the black hole is formed, or 1 million years after the black hole is formed, 1 billion, 1 trillion, 100 trillion years after the black hole is formed, depending on how close that particular vibration was to the event horizon. The closer it was to the event horizon, the longer it takes to escape. Eventually it does escape, travels, propagates, gets quote unquote promoted to be a real particle. So it's not about the formation of virtual particles with an already existing black hole. It's this very strange interaction between the vacuum of space and the formation of a black hole that has effects that linger for millions or billions or trillions of years. Hey, it's me again. I know you just watched a few minutes of me, but who couldn't use a little bit more me? I'm just here to beg you to please subscribe. And if I remember, there's going to be a button like right here where I'm vaguely gesturing so that you can click the button and subscribe, and it's super handy. This is so that you can get the latest updates of all my shows. I mean, that's basically how it works. So if you like what you just saw, you'll get more of it if you subscribe. Super easy.